Hello class. Today we have a new chapter. It's 10.1 and the chapter talks about the moment of inertia for areas, radius of gyration and their application and where do we use them. To begin with, let's define that the moment of inertia that we will cover in this lecture is going to be used later in advanced topic in dynamics, strength of material, and is very essential for those courses, as well as for the statics problems. The moment of inertia, or abbreviated by MOI, is defined by the integration of x squared over area if we were computing the moment about the y-axis. And the unit used for the moment of inertia, typically in the SI unit, meter to the power 4. Now, in many structures, probably you have seen different cross-sectional area designs, such as the H, the I, the C sections, and you probably were wondering what's the purpose of that? Why can't you use a solid cross-section instead of these shapes? Well, the answer comes from the resistance of such beams with these cross-sections. The resistance to the bending is more in certain shapes. And this resistance depends on what we call the moment of inertia, as we will see. Now, also other members which are made of tubes, or sometimes these tubes have square cross section. What's the difference between pipes that have a square cross section and a hollow yet, and also those which has a circular one? Now let's take a look at this simple submerged plate. A plate is submerged in a liquid. As you know, the pressure from the surface of water increases as the depth increases down. So if we choose the coordinate system to be on the surface of a tank or water, and as we're going down, the y is increasing in the positive direction, which is indicated here, down. The pressure applied by the water volume on a plate increases as we go down, and simply because the water head, or the amount of water above y is more. Therefore, we expect that the pressure will increase. So let's take a strip or a finite fragment on a plate and calculate the pressure on this strip. Now, the pressure is depending on first the specific weight. The specific weight for water and for any other liquid is known, and it's constant. However, the pressure will depend on the multiplication of the specific weight by the y, by the depth, where the specific weight unit, it's Newton per meter cube. When you multiply it with the y, it's going to give you Newton per meter square, which is a unit of pressure. So another way saying the gamma multiplied by y is going to give you a pressure, and that pressure is a function of y. Now, to calculate the force applied by that pressure on a strip, definitely we know the relationship between the force and the pressure is that force equal pressure multiplied by area. Since we are talking about the fragment or differential, then a differential or small force dF is equal to a pressure multiplied by the area dA for a small one. So therefore the pressure is related, or the force is related to the pressure in a small fragment by dF equal PdA. Now if we wanted to calculate the moment of this force about the x-axis, which is the tendency of the water to rotate this plate about the x-axis, we take the moment of these forces, which is, we agree, it's the distance multiplied by the force, and since we're talking about many fragments, so we do summation of all these fragments over the area, or in the simplest way we define the integration, which is the integration of y df over area, right? And we substitute the value of df, which is pda, and p is gamma y, so we end up with the formula that describe the total moment about the x-axis. Now, what does that mean? This integration, which is the moment of the area, we call it, will define the tendency of the force to rotate the object about the x-axis. So, and you notice that this is integration of y squared dA, which is going to be the tendency of the force to rotate about the x-axis. So this is the definition of the moment of inertia. So the definition came from that analogy, moment of inertia. Before we start doing some computation how to calculate the moment of inertia for different cross sections, let's take a simple application and really dig into what or why it's important to understand the moment of an area, or moment of second area, it's called commonly. So if we have a structure that is pivoted at R and simply supported at S, and there is a force acting on it, we know there is reaction forces, two reaction forces in R and one normally at S, and this P load tends to deflect the structure downward in parabolic or in curvature shape, like that, right? Like this, right? Now the question is, which one of these structures will have or resist this deflection, or have the least deflection? Well, it tends from the calculation that we will later learn that the structure that has the highest moment of inertia has the least deflection, or will have the least also stresses along the x-axis, right? So in fact, if we calculate the integration of the y square dA of these structures where y is in the y direction like that, we will find that it's the least for, or this highest for the A, and this is the least. Therefore, this will have the least deflection and least stresses, because the structure that resists deflection will have less deflection at the ends, and therefore will have less stresses. All right. So a couple of definition. And then I'll move to my handwriting to take some examples of how to do the integration. First of all, this definition is very important, not to mix the calculation of moment of inertia about the axis. For example, the moment of inertia about the x-axis means this x-axis means the tendency of this structure to rotate about the x-axis, and from here you can see that your integration variable should be with respect to y, right? So therefore Ix is integration of a y square dA. This also falls into for the moment of inertia about the y, which is the tendency of this object to rotate about dy, and to calculate that we need to know the distance of each fragment from this y-axis, which is x. So therefore here is integration of a dx. So remember that. So if you want to memorize it, then y and subscript means the sign integration is opposite variable. Mostly we'll deal with 2D problems. 3D is the same. It's not much a difference. Now another definition is the combined moment of inertia, and this is called the polar moment of inertia, which is as from definition, polar moment of inertia is the moment of this object to rotate about a point. So this is definitely it needs to measure the radius r, right? So the radius r. So this is called the moment of inertia, the polar moment of inertia. Now, there's a relation between r, x, and y from Pythagorean theorem, that r squared is equal x squared plus y squared, and that's because the integration can be distributed. This is gonna end up giving us that the relationship between the polar moment of inertia and the moment of inertia about x and y is following this equation, right? So this is equal to JO, right? So this means that you don't have to conduct this integration, just you can calculate each moment of inertia separately and then combine them to get your polar moment of inertia. Alright, so let's take this simpler problem, and we want to calculate the moment of inertia about x and y for the shaded area. Alright, so I'm going to take the screen and try to solve it together. So what we have is try to use different colors, a function. We are interested to calculate the moment of inertia of that function. The function is given by y to the power 3 equal to x squared. This is x and this is our y. And this function means this line, this curve. Okay, the boundary is from 0 to x. Now from 0 to x mean you substitute 0 here, you're gonna end up 0. You substitute y, and then y is equal to 1. So the boundary is from 0 to 1, and this corresponds to that. Now let's start with the moment of inertia about x. Moment of inertia about x means simply calculate the moment of this object about this x, meaning how much it's rotating, right? How much it's rotating. So the idea is to take a fragment or a finite element. This finite element is defining, this is our y, defining the moment of this fragment about x-axis, which is displaced by y. So that's the definition of the moment of inertia about x-axis. All right. Now we need to know how much is the dA. So this is the dA. dA has a height of dy and has a width. This width is this here, right? So how much is it? How much is that width? We know the distance from here to here following that curve. We know the distance from here to here is 1. So therefore it's the difference. It's 1 minus. Now the value of the x at this point is simply, look at this equation. So if you square root both sides, it's going to give you x equal to y 3 over 2, right? And we take the positive because we are in the first quadrant. So this is equal to y 3 over 2. Now, there's a reason why I want to always keep my variable in y, because my integration is y squared dA, so I have always to be consistent. And I put here 2 because that's the definition of the moment of inertia. If it was y, then we're not doing it, right? We're doing it for centroid. Alright, so then the dA is going to be equal to the width of the rectangle, which is 3 over 2, multiplied by its height, dy. So that's going to be equal y squared 1 minus y 3 over 2 dy, right? Continue. Now this obviously everything with respect to dy, so this becomes from 0 to 1. This from 0 to 1. Now our boundary is in the y from 0 to 1, from 0 to 1. This one, not that one. Okay. Alright, so we have to be careful. I know most of us tend to make mistakes during this stage of calculation, but let's do it right. Minus square is 3 over 2 plus 2, which is 4. I'm sorry, so plus 2, right? Plus 2 dy. Now this is from 0 to 1 y squared dy minus from 0 to 1 3 over 2 plus 2, so this is gonna be 4 over 2, so this is 3 plus 4, it's 7, so it's 7 over 2 dy. Okay, so that's now integration from 0 to 1. This is the boundary, minus 7 over 2 plus 1, 7 over 2 plus 1 from 0 to 1, minus 0, minus. So this is 2 over 2, this is 2 over 2. So this is 9 over 2 becomes 2 over 9, right? So this is 1, 9 over 2 minus 0, 1 over 3 minus 2 over 9, and that's going to give you 0.111 meter cube. I'm sorry, to the power 4. So that's our first moment of inertia about x-axis. Alright, so now we want to calculate the moment of inertia about the y. By definition, I want to calculate the moment of this shaded area about its ability to rotate. So I'm looking at a fragment such as this one to rotate about the y-axis, right? So this fragment has an area of dA, a width of dx, and a height. This height, for my best interest, I want to define it in the x, because the definition is how this fragment is rotating about the y. So the distance squared dA about the area. So this dA has to be in everything in x so that I can do the integration. Great. So looking at that, so I'm looking at the height, this height. So the dA equal to dx multiplied by that height. That height is easy because it's equal to, this height is x square 1 over 3, this is equal to y from that equation, right? So dA equal to x square 1 over 3 dx. dA equal to x 3 dx. So ay equal x square x 2 over 3 dx, and the boundary is from, because it's dx, from 0 to 1, from 0 to 1. So that's it. I mean, if you get to this point, you are done. The rest is calculus. It's equal to 0 to 1. Now this becomes addition, so 2 over 2, sorry, it's 4 over 2 plus 2 over, oops, I made a mistake. Try to be fast, but that's a good idea. It's not a good idea. It's 2 plus 2 over 3 dx. So multiply by 3 over 3, so this becomes simply, so 3, so it's a 6 plus 2 over 3 dx, and that is equal to 0 to 1 x 8 over 3 dx equal to 1 over 8 over 3 plus 1 x 8 over 3 plus 1, 0 to 1, and that's equal to 3 over 3 become 3 over 11, right? X 11 over 3 minus, over here, from 0 to 1, 3 over 11. This is actually equal to, this is 1 minus 0. So the answer is 3 over 11, which is approximately 0.273 meter to the power 4. Now if I ask you to calculate the polar moment of inertia, you're going to say it's Ix plus Iy, and that's equal to, from previous it's 0.11 plus 0.273, and that's going to be meter to the power 4. And the polar means, you know, how this tends to rotate about O, right? So that's it for the integration. So the remaining of the presentation, there is more questions, as you can see here. You can go over it. I think the main idea you got it. It's easy. There's a group problem solving. I encourage everyone to try it at home. Same concepts, nothing is tricky. With that, we conclude this today's lecture, and I'll see you next Thursday. If you have any question, remind me at the beginning of the class. Thanks.